Okay, this is second part of chapter 15. These are Kepler's laws, and Johannes Kepler in the picture here came before Hooke and Newton and the work that they produced. Newton eventually got the fame for, which is Newton's law of gravitation. So that's the main idea behind the first part of the section. However, there's some very profound stuff, and in this section, a derivation for you to do as well. Okay, so this derivation you need to know your way through. So we left it here with the ideas of gravitational fields and gravitational field strength, and it was Kepler who, before all that, had made some observations based on work he was doing with a guy called Tycho Brahe. Now, I've put a lot of the detail, I've mentioned a lot of stuff in the PowerPoint, so I'm just going to flick through this a little bit. So he realised several things from the observations that he made, or rather from the mathematics and the positions of the observations made by Tycho Brahe. He came up with these three laws, and as things passed around, for example the local planets passed around the Sun, he realised that they weren't circular. They had this perihelion where they're closest, and then aphelion or aphelion where it's furthest away, and that circles aren't quite the correct path. That was the only way to explain these mathematics. Now, a circle is a very specific type of ellipse. This is an ellipse. It is a circle with two centres. If the two centres, the two foci, align in the middle, then you get a centre. That is a centre of a circle. The rest of the time, you're still getting the same shape, you're still getting the same mathematics, basically, but you have a two-centred circle. So Kepler's first observation was that all planets, and for them at the time that only went out as far as Jupiter really, but all planets move around the Sun in, and the spelling on this is always confusing for people, elliptical or ellipse, double L, elliptical orbits with the Sun at one focus. One of the foci. Okay. So two focuses, foci in plural. The Sun must be at one of them, and we find the same with everything. So if you play the PHET animation, you'll see that we move around the Sun moves around us, we move around the Moon just as much as the Moon moves around us. It's just one of them moves quicker because it's less massive. Now, what he also realised is as he went round, it got faster, so it swept through a bigger radius, a bigger arc length, sorry, as he got closer to the Sun. Then it slowed down. This is very obvious with comets, so if you play again the animation from PHET, you'll see that very, very obviously. But what he realised, again mathematically, is that they actually swept out the same area, so there's a lot more to it. So his second law is that any radii, so again any line like this, between a planet and the Sun. Now again, I should say for A level, this works in all systems, it's not just us, but at the time he was saying about the Sun because that's all we knew. So any radii between that and the Sun sweep out an equal area. Okay, and that's the crucial bit, in an equal time. Okay, so that gives us a bit of a description where the mathematics then comes from, and then can be explained using Newton's laws and this idea of gravitational field strength. But these observations are really quite profound. You will need to know these. Okay, so just visualise them and then you'll be able to put them into your own words. That's not too difficult. It'll be an ellipse and they speed up to sweep out a bigger area, a bigger arc length, therefore the same area for every second or hour or year. Now, the important bit is Kepler's third law. And we're starting to get into the idea of what's going on. He spotted patterns in the timing, hinted at with this one. He couldn't come up with the mathematics, and it was Newton that came in for that reason later. Okay, so for it to work, we know that things basically going in a circle, an ellipse will do as a circle for us because most things are fairly circular, the two foci are close together. So we'll say it's going in a circle, and for that to work we need a force inwards. That's where the gravitational attraction comes in. So using what we know already, then we can have, we put together two facts, which is if we're looking at centripetal force, we can have mv squared over r, or of course m omega squared r. I personally think it's easier to do that one, but again, either will do. Again, in the PowerPoint, it tends to do this one. Fair enough, it's easy enough. So, gravitational force, well, that's minus g, big M, little m, over r squared. Okay. Now, if it's in equilibrium as it goes around, dynamic equilibrium, then these forces must be equal. The gravity is what's giving the centripetal force. Therefore, for something of that mass moving at that speed in that much of a radius, that happens to be right by Newton's first law of gravitation. So if we take those, it's the next steps are actually fairly straightforward. You just need to be a little bit clear with your maths. So if we think about what's going on here, we can work out stuff fairly easily. I will go with the v squared one because it fits with the PowerPoint, so don't get some confusion there. We do need our g. What we can do straight away is we can get rid of m, the little m. So this doesn't matter what mass of object is in orbit, the whole thing will still work. It all depends on the mass of the thing at the focus, so the sun for the planets. Doesn't matter on the size of the planet. Radius, well, one of those would count as well with that. So we can end up with, quite simply, v squared equals minus gm over r. Okay, so let's call that equation 1 because we'll come back to that. So we can do the basis of that. If you've ended up with omega squared, well, it will just give you a slightly different format. It will give you r cubed. R cubed is actually the answer anyway, so there's two ways of doing this. Now if we use this version, we need to find the velocity. Well, because we know that, we know the radius and we know that, so let's kind of link everything together to give the pattern that he spotted. So using S equals ut or vt, we know that 2 pi r is the circumference of the circle, happens to equal the velocity it's going through, and t for one time period, so capital T because it's going all the way round. Okay, so what that means is if we substitute it into equation 1, what we end up with is v squared equals minus g capital M over r. Be careful you don't get the wrong thing in there. Okay, we're going to end up with that rearranged a little bit, 2 pi r all squared. Okay, so we need to get that in there because it's v squared, and it'll be t squared as well, so divided by t squared. Now obviously you can do that in one lump, but there we go. So just to make that a bit easier, I'm going to go for gmt squared, don't forget the minus, equals, and I'm going to multiply everything out. So I've got 2 squared, which is obviously 4, pi squared, r squared, multiplied by r, so r cubed. What we end up with is we get Kepler's third law from this, in that he spotted the variables long before we got to the equation. So he realised just from observations that time squared for the orbit of a planet is proportional to the radius cubed from that focus. So I'll just put it in there, giving Kepler's third law, I should say, in that t squared equals 4 pi squared over gm, and again we've got a minus in there if you want a direction of forces, but it's just showing it's attractive, so I'm not going to worry about that. Oops, it's r cubed. I will put modulus though, just to make it clear, which was that t squared is basically proportional to r cubed. Okay, and as I said there right at the beginning, and is independent of m of the planet. Okay, now that gives us a whole host of things, but it's not just about planets in motion, it's any satellite. And for us, we use this all the time still when we're talking about man-made satellites. So a little bit of linking. I've split it up in the PowerPoint, so it's a separate PowerPoint, but we can use satellites that we put into space to do certain jobs still using this same system. And you may be asked to kind of talk in the round about this. They might give it as a context, but the idea that if you are smaller, you have a smaller radius, if you're closer into the planet, then your time of orbit will be much, much smaller as well. Obviously, these are just using these forces up here, so if we start getting friction, if we start bouncing off the atmosphere, that's a different thing completely. The whole lot will change. However, if you're out in space where there's no friction or no restricting force of any variety, then this will always hold clear. So, again, in the 2B PowerPoint, I'll give you a bit of background about Arthur C. Clarke and his ideas, but we have a lot of communication systems that are in orbit in the same position. So our course calls them geostationary, but it's also, more correctly, geosynchronous. It's EOS. Trying to say that and write at the same time. Geosynchronous because the motion is synchronized. It's not stationary, it's synchronized with the Earth. So to do that, if we get something in the right position and moving in the right direction, so it needs to be orbiting in the same, I'll just put in angular just to make sure, angular direction as the Earth. I'll put the planet, though we are mainly talking about Earth here. It needs to be orbiting around the centre of the planet, so it needs to be orbiting above the centre of mass, the centre of the sphere. But for it to stay still above the same spot, then the only place that will work is above the equator. So it has to lie above the equator. Otherwise, again, a diagram in the PowerPoint, it would move up and down in the sky as the Earth went round. So it lies above the equator with, and this is a fairly obvious one, I think, with a 24-hour time period. Okay, if it wasn't 24-hour, it wouldn't stay in the same spot in the sky. Now, if you do the mathematics of that, stick that in, we know the mass of the Earth. Again, you can look it up, it's not hard. We know the value of g, 4 pi squared. What radius would give us 24 hours squared? I should add that has to be in seconds, of course, but again, in your data book, you've got the number of seconds in 24 hours. Okay, so I'll leave you to finish this. So, at a height of, and we'll go with kilometres. Obviously, your answer will be in meters, but that's quite big. And that's the 24-hour period. Okay, again in seconds. So put that in, but notice the trick. That's often how we'll give it. What you will calculate is the radius, so you will then need to subtract from your total distance, you need to subtract to the surface, so you've then got the actual height above the surface itself. So just put a start in there, note, not radius. Okay, so all your calculations always be on radius, but now this is good. This covers a fair amount of Earth. We can communicate. We can have our satellite TV dishes bolted at the same angle to the house, pointing at the same bit of sky, because these appear to be stationary. However, it doesn't see the whole surface, so often we will need scanning satellites that will cover the whole surface. I had a friend who worked out in Antarctica for 3 years, and basically the only way to get messages out to him was through a low Earth orbit, which goes over the tops, North and South Pole, and as the Earth spins underneath it, it sees different parts of the surface. So what you'll find is that you could see all parts of the surface, and every time it went over the Antarctica bases, it would transmit down to them, so they'd not have continuous communication, they'd have to do batches, but it's still possible. More importantly, this idea to move across the planet's surface, seeing strips of the surface, means they're brilliant for surveying things. And it doesn't matter what it is, whether it's crops, whether it's desert, whether it's earthquakes, man-made issues, whatever it may be, you find that this is really, really useful. Not only that, but if you get it to spin at a lower height, a lower radius, they'll spin more frequently and they'll make more scans of the Earth. And so from that you can get a lot more detail, and obviously a bit lower means that the resolution of their cameras being closer to the surface will also give a better image, or a smaller image detail, than without actually changing the camera itself, than one that is higher up. So really, really useful. It links in with the ideas that we're going to build up to at the end of the topic, and that is these have, I said it's lower altitudes, okay, which means it requires them to move more quickly, okay, but they have higher kinetic energy. Why? Because they've less gravitational energy. So all that work we've done, and you've been doing for many years, about kinetic changing into gravitational energy and back again, it's still the same, more complicated because it's not a linear field, it is a radial gravitational field. So we'll get into the mathematics of this, which is probably the trickiest bit of the whole chapter, but really, really important idea, just to go back to the fact that it's actually quite simple behind the scenes. You know, the energy must be constant, therefore if you're going faster you must have less of the other one. Okay, so bearing that in mind. Why is it useful? This hint that I've just given there is that basically as the planet rotates, or rather the planet rotates underneath, okay, their path, so underneath the orbit, and so the let's put the satellites, they can scan slices, rather like you see of a globe when you open it out, you see kind of lemon slices almost. They scan slices of the planet's surface. So whenever we send out a probe to any other planet, if we send it out to scan around the sun, whatever it may be, because the sun rotates just like a planet, then if we get it to go into polar orbit, you actually see much, much more than if you just try and move it around the equator of it. So you want to scan as much as possible, see what's going on. So, a couple of ideas there. Worth reading around both of these to get the main background to and a better understanding of what's going on with satellites and probes in space. But this is the bit that you'll really need to make sure you know about, stating Kepler's first two laws and being able to derive the third one, which isn't difficult, because we've done a lot of work on centripetal force already and it's moving in a circle, approximately. Okay, so the mathematics works through. You just got to remember how do you get rid of the v, or of course the omega, which would be 2 pi divided by t. So very, very similar process. Yeah, I'll leave you to figure out that if you want to take that approach instead, which I think is a little bit easier, equally valid. Okay, thanks very much, guys.